So in this video, we're going to look at this classic ice to steam problem that you will come across quite often in engineering studies. And in our example, we have our ice measured at 0.22 kilo for its mass, and its initial temperature is at -5 degrees Celsius, and it's going to be heated continually until it turns to water and eventually turns to dry steam. And what we're tasked with is to evaluate or to determine the total heat supplied. And we're given some important metrics here. So these quantities for specific heat capacity of water, which measures how much energy it will take to raise the temperature of 1 kilo of water by 1 degrees Celsius in this case. And we also have our latent heat, and the latent heat here is the heat required to change the phase of a substance. So if we're changing from ice to water, or from water into steam, then we look at the phase change in terms of its latent heat. So let's go ahead and analyze the problem and see how much the total heat supplied will be. Now, the first thing I'm going to do here is to evaluate how much energy it will take to convert the ice into water. And the formula that we use for that is Q, which measures here heat energy, equals M for mass. And we're going to use here L for latent heat. But the specific one here, the type of latent heat we need to use at this stage, is the latent heat of fusion. So you will see this subscript F, which stands for latent heat of fusion. Now our mass, which is M, is 0.2 kilo, 0.22 kilo, and our specific latent heat of fusion is 335 kilojoules per kilo. So you have to ensure that you write this as 335 and multiplied by 10 to the power of 3 because it's kilojoules. And our final answer there will be, so that's 73.7, and I'm going to write this as times 10 to the power of 3 joules. You can write this as kilojoules as well. So that's the first state there. Now, if we're now moving from ice to water, so that's the energy that it takes to move from ice to water. So what we need to do now is to calculate how much energy it will take to raise the temperature of water to its boiling point, which is going to be to 100 degrees Celsius. So now this bit is raising the temperature to 100 degrees Celsius. Now for this, we have this formula that says Q, again for heat energy, equals M for mass, and C here, which stands for specific heat capacity of water in this case, which will be multiplied by the change in temperature. So if we just substitute our quantities here, we will end up with the same value for mass, so that's 0.22 for mass, multiplied by our specific heat capacity of water, which is 4.12 kilojoules per kilokelvin. Multiply that by 100. So then our answer here for our heat required to raise the temperature to 100 degrees Celsius is going to be 92.18, and it's going to be again times 10 to the power of 3, so that's joules. So that right there so far is our water temperature, the temperature of our water now raised to 100 degrees Celsius, and that's the highest we can go. So from here on out, this is where the water will now be converted into steam. So let's go ahead and look at that. Okay, so to turn the water into steam, you notice that the formula looks very similar to the one that we use to turn the ice to water, but this time we have L and subscript V, which stands for specific latent heat of vaporization, because we're gonna get some vapor at this point. So when we multiply out our quantities now, we have 0.22 again for our mass. And be careful now with the specific latent heat of vaporization, because all along we have been using times 10 to the power of 3, but this is megajoules now. So this will be 2.25 and times 10 to the power of 6 this time. So what this will give us here is 495 times 10 to the power of 3 joules. So at this point we have one last thing to do, which is to evaluate the total heat supplied. So let's go ahead and do that now. So for our total heat, we're just going to sum everything up. So what we have here is our 73.7 and multiplied by 10 to the power of 3. Add to that, we're going to have our 92.18 and multiply that by 10 to the power of 3. And then finally we have our 495 times 10 to the power of 3. Now, because all of these are written in standard form and we all have the times 10 to the power of 3, you can simply multiply, or you can simply just add those decimals up. So what we end up with here is 660 and 0.9 times by 10 to the power of 3 joules. So this here will represent our final answer, and if you want to, you can also write it in terms of kilojoules. So 660.9 and write common K, capital J, so that's kilojoules. And this here represents the total heat supplied to convert our 0.22 kilogram of ice into steam. So in the next video, we're going to look at this heat exchanger problem. So have a look at that video and I'll see you there.